So today we'll be talking about the mathematical derivation of the voltage gain of a common source JFET amplifier. This is just a basic electrical circuit. Now, this is a common source amplifier. Why is it called a common source amplifier? We can recall that a JFET amplifier has three terminals, which is the gate, the drain, and the source. Now, it's called a common terminal when a particular terminal is common between the input and the output. If you look at the input, you'll see that the input voltage is connected between the gate here, and it is grounded here. The source is grounded here, so it means that the input is connected between the gate and the source. The output is connected between the drain, and as well the same way it is grounded here. So it means the output is connected between the drain and the source. So we can see that the source is common between the both of them. So it is called a common source amplifier. So our aim is to derive the voltage gain of this amplifier. The voltage gain is the ratio of the output voltage to the input voltage and is expressed mathematically as. Now this is the expression for our voltage gain. Now I want to consider an equivalent circuit of the circuit we just saw just now. This is going to be the equivalent circuit of that. This is actually going to be the equivalent circuit of what we just saw just now. Now, this equivalent circuit usually looks like this. In our next video, I'm going to show how to derive this equivalent circuit. So let's move on for now. Now, you must know that the current from the current source divides between the internal drain resistance and the external. Let's explain what that means. This is the internal drain resistance, that's the internal resistance of the transistor, while this is the external drain resistance. You're already seeing that this is the drain and this is the gate. This is the controlled current source. So when this current gets to this point here, it's divided into two. We'll have one through the internal drain resistance and one through the external drain resistance as seen. Now, by using the current divider rule, the current through the drain resistor, that's the external drain resistor, is giving us this. If we use the current divider rule, we are going to have this expression for the current through the external drain resistor. And similarly, through the internal drain resistor, we are still going to have this. This is the expression through. This is internal. This is internal, and this is through the external drain resistor. This is external. So this is the external and this is the internal. By KCL rule, the sum of these two currents together, the sum of these two currents must be equals to the controlled current source, which is the transconductance times the input voltage. Now you can see it here on this particular diagram. This is the controlled current source again. This is the current comes like this and it divides it to one in this direction and one in this direction as so seen. So one current goes through this and the other goes through this. The output voltage, which is this is our output voltage, is going to be equal to the negative of ID times RD. This I of D we are talking about is going to be this, we are talking about this current actually. So if we substitute this into our equation, we are going to have this expression. V naught is equals to negative GM times this, where we have rearranged a bit, so RD will meet this. If RD comes this way here, we are going to have this resulting equation. Now, if we divide through by this, that's V naught divided by VGS, we are going to have this expression here. So our voltage gain will be given by this negative GM into bracket RD, which is parallel. You can see it from there, here, and here in our diagram, that RD is parallel to small RD. And if they are parallel, then this can be replaced with this. It can be replaced together. Now here, this is our external drain resistance, this is our internal drain resistance, and this is drain resistance, please. Internal drain resistance. Then these are our transconductors. For an ideal voltage gain, it means that the internal drain resistance is extended to infinity, is very, very high. And if it is very, very high, it means all the controlled current is going to pass through the external drain resistor. And we are going to subsequently have our voltage gain given by this expression. Now let's see a problem. It said a certain JFET amplifier has a transconductance of this. If the load resistance is this, and they gave us the inputs, this is our internal drain, this is our internal drain resistance, and this is our load means external, this is our external. So we are asked to calculate the value of the voltage gain. Now by solution, this is our formula for voltage gain here. So this is the parallel resistance relationship as we had just now, which is capital letter RD times small letter RD all over capital letter RD plus small letter RD. That is our relationship we used for this here. So if we impute what this expression is, and GM here is GM, and if we impute this as well here, it means that our voltage gain is going to be negative 2.4, negative 24.5. So we are going to solve more problems in our next class.